Next, we're gonna see how to define functions from scratch. We start with the definition of Cartesian product A times B. This is the set of all pair of points A and B. For A is an element in set A and B is an element in the set capital B. So the function is defined as follows. Let A be set. A function from A to B is a set F, which is a subset of this Cartesian product A times B, such that for each A in capital A, there exists a unique B in capital B with the pair AB inside this set F. So a function is basically a subset of the Cartesian product. And the domain of this function is the set of all elements A in capital A such that the pair AB is in the subset F, and the range of the function is the set of all B in capital B such that the pair AB is in the subset F. Clearly, we see that the domain of the function is exactly the set A, while the range of the function is a subset of the set capital B. For a subset E in A, we can define the image of E under F, and this is the set of f of x for x in E. For subset H in B, similarly, we can define the inverse image of H under F, and it is denoted by this symbol. And this is a set of x in A such that f of x belongs to H. So here is an example. We consider a set from, we consider a function from the set of real numbers to itself such that the function here, remember, is a subset and it defined follow. It is a subset of all the pair x and x squared for x in R. So in calculus, we say f of x equal to x squared. And for the example, the domain of the function is just the set of all real numbers. The range of the function, on the other hand, is only consists of non-negative numbers. That is, it is a set from 0 to infinity, including 0. And this is a proper subset of the set of real numbers. Here we can take a set E, which is the set of all numbers between 0 and 2. Then the image of E, f of E, is the set of y equal x squared with 0 smaller than x smaller than equal to 2. Then this set is equal to is the set of numbers from 0 to 4. Similarly, we can consider the subset H of numbers from 0 to 4, and this is exactly the image of the set E, and we consider the inverse image of this set H. And so the inverse image here consists of all number x such that 0 smaller than x squared smaller than 4. And we can easily deduce that x here must be between -2 and 2. That's why the inverse image here is a set of numbers from -2 to 2. So we observe that the inverse image of the image of E is not equal to E. So that's something to remember. So That's how a function can be defined from scratch. Here are some properties of functions. First, we start with definition. A function is one-to-one or injective if whenever x1 not equal to x2, then f of x1 is not equal to f of x2. In that case, f is called an injection. A function is onto or surjective if f of a equal to b equal to the range of f. That is, the range of the function is the whole set B. Remember, in the original definition, the range of the function is a subset of a set B, and the function is onto if this subset is actually equal to the set B. And in that case, f is called an injection. And when the function is both one-to-one and onto, we call it a bijection. And here an example. Again, we consider the function f of x equal to x squared. And easily we see that this function is not one-to-one because f of minus 2 equal to f of 2 equal to 4. So here we have two different inputs, minus 2 and 2, with the same output 4. And also the function is not onto because there's no x such that x squared equal to minus 1. So minus 1 here is not in the range of the function. Now, let me define an inverse function. If f from if the function f from a to b is a bijection, then the function g, which is defined as the reverse order pair ba in the Cartesian product b times a for the pair ab in f equals inverse function of f. So basically, the inverse function is just the set of reverse order pairs of the original function. So for example, the function f of x equal x plus 1. So denote the y variable here equal to x plus 1. Then we can deduce that g of y equal to x and equal to y minus 1. So g here is the inverse of the function f. Another very important notion about functions is the composition of functions. That is, if you have function f from a to b and a function g from b to c, then you can define the composition of g composed with f. And this is going to be a function from a to c, and g composed with f evaluating some input x is equal to g of f of x. So basically, we apply the function in the correct order. Again, here is an example. Here's a function fx equal x plus 1. This is a function from the set of real numbers to itself. And then the function g of x equal to x squared. Again, a set of function, a function from the real numbers to itself. Then the composition of f and g equal is evaluated follow. It's gonna be equal to f of g of x. G of x equal x squared, so it's gonna be f of x squared equal to x squared plus 1. On the other hand, if you consider the composition of g and f in that order, then this is gonna be equal to g of f of x. F of x equal x plus 1, so this is equal to x plus 1 squared, which is equal to x squared plus 2x plus 1. So clearly we see that the composition of g and f is not equal to the composition of F and G.